in this case ethanol, you'll get ethanoic acid. Okay? Okay, so well done, Max. You've done your bit. Can anyone suggest what we could do next? Adjustment.
Well, I know you need like a diol and a dicarboxylic acid.
No, you're overcomplicating it. Overcomplicating it? Yeah. Yeah, just mix those two, react those two together. And together, a carboxylic acid and an alcohol will give you your ester that you want. So, right now, you may be saying to yourself, what on earth is this guy talking about? Okay? I'm not expecting you to know that. I'm not expecting you to know that yet. Okay? What I am expecting you to realise is to try and be able to use your brain to think, how can I manipulate what I'm starting with? What reactions do I know that ethene does, alkenes do? What can I produce from the alkene? And how can I use that to make the product I really want? So it's expecting that it won't be a one jump from the left to the right, but actually you'll have to go through a few stages. Okay, that's all I really wanted at this stage, for you to understand. Now, normally, if you really want to do organic synthesis really well, the next thing you would do is you take all these compounds, alkanes, alkenes, alcohols, arenes, which you don't even know about yet, halogenalkanes, aldehydes, ketones, carboxylic acids you've heard of, esters you've heard of, and something called amines. And what you would do is you'd literally do this. You go, right, okay, what reactions, guys, listen, what reactions do I know of alkenes? Well, I know that they undergo addition reactions with bromine, and you kind of give your product, general product of the reaction, okay, a bit like that, and you go through and you produce a diagram with all these different reactions. So it's a good way of reminding yourself, how do I get from alkenes to something else? And then what can I use that product for? I could say, well, up here I've got a halogenoalkane. Look at my halogenoalkane, see what I can produce from that. But at this stage, you're not going to be able to do that. So don't worry too much about that. But one thing you need to know about, in order to do any of these problems, is what on earth that means. Luckily for you, I have got a sheet, but I'm not going to hand it out now. What I'm going to do is I'm going to give it to you at the end. I'm going to put it on the table and you can all help yourself. But it's a sheet that explains how to do this. So I am going to explain what a skeletal formula is. It's called skeletal, okay? And it's basically because chemistry teachers, chemists, full stop, get really bored of drawing out carbons and hydrogens. And anyone who was probably in my class at GCSE and had to write out all the different isomers of various different things also got pretty bored of writing out all the carbons and hydrogens. So this is a shorthand way of writing a carbon chain without having to do the carbons or the hydrogens. So if you look at the one on the far right, and I hope you can all see that one, that actually represents a chlorine joined, the next one to its left is a carbon. See where the O comes down with a double bond? That is a carbon with a double bonded oxygen on it. And then as you come down to the left, there's another angle, isn't there, where it sort of goes round a corner. That represents another carbon. But this is simply a carbon in a carbon chain. So that carbon will have something else on it that we haven't included. And if I'm trying to explain it verbally because I know a lot of you can't see this very well. But if I drew this out in full, that one on the right-hand side, it would simply look like this. It would be chlorine joined to a carbon, double bonded to an oxygen. And then down here we'd have another carbon, and then we'd have a fluorine. Okay, I'm going to draw the fluorine here, I think. Okay? Now the question is, we know we've got a carbon there, but how many hydrogens do we need? Two. Because it's already got two bonds. So that is That is the longhand way of drawing that thing on the right-hand side. Now you might say, well, that hasn't made it that much shorter. But if you've got 10 carbons in a chain, believe me, it's a lot easier to do that than it is to write carbon, double bond hydrogen, 2 bonds hydrogen, all the way down the chain. Now I'm going to go next to the one on the left-hand side. Who'd like to suggest to me what that might look like if I wrote it out in a more full hand? So the one on the far left. Go on, Ishwan.
Would it be CH3, CH2, O, C, O, then CH2?
You're right. CH3 is that? Yep, it's the end of the chain. Yep, that is exactly right. The ones you've got to be careful of are the ends of the chains, because where it stops, those are CH3s. They're carbons with 3 hydrogens on it, and it's always a CH3 at the end of the chain. If it's in the middle of the chain with no substituent groups like fluorines or chlorines or OHs, it'll be a CH2. So this one goes CH3, CH2, O, C, double bonded to an oxygen, and a CH3 off to the right. Right. What about that middle one? Now that middle one has something that you've probably never seen before. It's a hexagonal ring. Does anyone like to put their hand up and tell me what that is? It's a benzene ring. And if you've never heard of a benzene ring, that's perfectly okay at the stage you're at. The benzene ring looks like this. If you were to draw it out properly, it's got 6 carbons. So it forms, I'm terrible at drawing these, it's a hexagon. And each of the carbons has a hydrogen on it. And depending how you see it drawn, you either see it with a circle in the middle, or as they've drawn it, it's called the Kekulé structure they've drawn. They've got alternating single and double bonds, like that. Okay? So that is basically, if you look at each carbon, it's got 1, 2, 3, 4 bonds. Every single one's got 4 bonds. Okay. And the stuff at the top, we take off one of the hydrogens, because we're going to attach it to a carbon, which has a double bond and an oxygen, and then a CH2 and a CH3. This time they've put the CH3 in there, haven't they? Right, so that's what that looks like. So just remember, every corner, every one of these corners will be a carbon. The end and the corner will be a carbon. Okay? And hopefully then with the stuff we're going to do today, it'll make some sense to you. Right, okay, so that's that. Now, you are going to face, in the Olympiad, as we said, you're going to waste a lot of time otherwise. Danny? Now that is a typical kind of molecule you might be faced with in the Olympiad. And the thing you mustn't do is look at that and go, whoa, I can't do that. That's far too difficult, okay? What you've got to do is try and stay calm and say, right, what did Mr. Rogers say? What can I remember? And already on what I've told you, some of this will make sense. And even actually, now that you've done a bit more of the initial stuff in year 12, things like what these wedges mean will make a bit more sense. So, Tane, you know about wedges. What does that mean?
Well, basically, it's like representing it in a 3D plane. So the wedges mean it's coming out. Maybe, yes.
So these ones are coming towards you, sort of out of that kind of an angle.
And then the dotted lines are like going into the face.
That's right. They're either dotted or they're a bit like the one at the top where it says CH3, where they're sort of like that, going backwards. Okay, so sort of sloping back into the plane. Okay, what else can we tell from this information? What do you think all these things are? They're not benzene rings, but what might they be? You tell me, what is that there? That's the CH2, isn't it? It's just the corner CH2. Now you've got to be a bit careful here. That's not a CH2. It's just a C with one H, this one here, it's a C with that H on it. And the other H has been replaced by an OH. Okay, so it's got two groups here already, plus the two bonds there. Normally if I have this on the board I can actually point to it, I find it really difficult to say. Right, okay. Other than that, where it's got two lines, that's a double bond. So actually, you can kind of understand what that diagram is all about. If I asked you to draw it out like this, you could probably just about do that. Okay? So, you know, if you're faced with a complicated molecule, and you are going to be faced with one today, don't panic. Right, okay. So, how do we do organic synthesis? The best thing, and the thing I'm going to really encourage you to do, is to check, first of all, not only the number of carbons you've got in your starting material in your product. So say you're going from A to B, you've got to work out whether the number of carbons is the same or whether you have to increase the number of carbons. So if you're going from A and it's only got 3 carbons and B has 4 carbons, you're going to have to find a way, aren't you, of putting an extra carbon up, okay? So that's where the logic comes in, and you have to think about how you could do that. So if the number of carbons increases, you might well be reacting 2 different molecules together to achieve it. Always write down the starting molecule and the target or product molecule and see if you can spot a connection between them. Yeah, it may not be 1 step, it might be 2 steps. And sometimes it's good to look to see what's at the end, because you can then work backwards to work out what you got at the beginning. Okay, so that's called retrosynthesis. I'm not going to go into that in any great detail, but by looking to see what the product looks like, you can sometimes work out what has had to happen to it to make it from the reactant. Okay. As I said, above all, use logic. Now, what we're going to do is I have to give you each one of these. So I hope I've got enough, because I've got 35. You're going to look at this and go, what is he asking me to do? But please just bear with me. Right, take this, have a look at it, and I'll tell you what you're doing in a second. Don't go shooting ahead yet. Okay. What I'm going to do is I've got a slide with this on, so you'll all be able to see in a minute, but I'm going to go and photocopy a few more, but just listen for the moment before we get started. So you have to start, you'll see this is a whole synthesis, starting from A, going all the way down to, what is it, J or K, something at the bottom. You have to do 1 step at a time. Compare the molecular formula of A, I'm talking about A to B now, and see what's changed. So I'm going to explain. Right, here's the thing that's on these sheets, so I'll get you the rest in a minute. Can we all just look at the board for a minute? Here you've got A at the top there, and B over to the right. And above the arrow, there's a reagent, a chemical that's used to convert A to B. Now, you have never seen that chemical before. And to be honest, I've never seen it other than on this problem, so I don't know much about it either. However, I can still solve this, because the way I do it, I work these out, it's completely logical. If you look at A, what's the formula of A? It's C9H14 N2 O2. And then we go to B, it's C10 H16 N2 O2. So then I say to myself, what has changed between going from A to B? Okay? So what extra groups have we got and what have we lost, if we've lost anything? So anyone like to tell me what's the difference? It's one simple unit that's kind of been added in. Okay. Someone who hasn't said anything yet? Is that you, Adam?
No, I was thinking.
Oh, right.
Well, no, it is CH2.
CH2. It's the difference, listeners, the difference between the two is C and two H's. Yeah, you can write on the sheet. Yeah. Now, this is for the benefit, I'm trying to make sure these guys can still see what's going on. What I did next in my little brain is I said, right, I've got to somehow put a carbon and two hydrogens into the structure, but where? Because I don't know anything about this thing on the left-hand side, A. So I thought, well, okay, where else have I got some information? Well, I could look at C. Because C is where we're going next. Would anyone like to suggest where that extra carbon might have gone, looking by comparing A and C? Just have a quick look. I'm not going to take the answer yet. Just have a quick look.
That is so not.
Right, has anyone got a suggestion where that extra carbon might go by comparing A with C? There's only two changes between A and C. Two real changes. You look at the structures, only changes are in two places. Dimitri, can you suggest where one of the changes is if you were to compare A and C?
Well, at the very top, for the A, it's just like CH, and then when C it says CH3.
Good. So we've taken off an H and replaced it by a CH3. Okay? Now I instantly say to myself, okay, so we've lost one H, but we've gained a CH3. So the difference between what we had before and what we ended up with is a CH2, isn't it? It's a net difference of one carbon and two hydrogens. So that is likely to be where the carbon is going to join onto my structure in B. And actually, the other change wouldn't achieve that at all. In fact, you're losing some carbon. So that can't be it. So I can already work out what A to B is without actually knowing anything about the reagent, CH3 to SO4. Okay? So what I'd like you to try and do is, on your sheet of paper, if you've got one yet, to try and just sketch what B looks like. So do a quick sketch of that with changing it to a CH3. And then try and work out if you could, what happens between C, B and C, and then C and D while I quickly photocopy these extra sheets. I'll be back in 2 minutes. Apologies about the technical things. Anyway, has anyone worked out what's happened between B and C? What's the big difference? Okay, have a look. Can anyone tell me anything that's happened? You guys. So C2H4.
Yeah, because there's two extra. No, sorry, not added, taken away.
Okay, so C2H4, yeah, I think that's right, is H5? H4. C2H4 has gone. Where has it gone from? Ellie, can you see where it might have gone from? So it's lost 2 carbons and 4 hydrogens from somewhere. Look at A and compare it to C. Where, sorry?
Next to the oxygen.
Next to the oxygen, yeah. Listen, everyone. It's those last 2 here. They've gone. Okay? So, this is where it's a bit more complicated for you because you won't necessarily know what the question mark is. But what you can do, this is an ester. If you look at this, you will recognise an oxygen joined to a carbon with a double bonded oxygen. So that's an ester. And if you boil up an ester with acid, you can actually remove the alcohol, the original alcohol bit, this bit here, and replace it with an OH. So you won't necessarily know that, but you can see that that's what you've done. You've removed those last 2 and replaced it with an H. Okay? So that's got us to C. Now, I'll be honest with you, this next, from C to D, the next reagent, someone in year 13 should be able to spot, because they use that in as a reagent for what we call nitrating benzene, which means we put an NO2 group on the side of benzene. Now we haven't got a benzene here, but what we do have is something that looks a bit like it. It's a ring structure. So I'm going to give you a clue and say you're going to put an NO2 onto that ring. Now if you didn't